Hi, welcome to this video where I will be showing you the uh, demonstration for statically indeterminate structure in a finite element software MIDAS Gen. As we saw in the previous three tutorials, we dealt with statically determinate structures which are easier to analyze using hand calculations also. But when the indeterminacy it comes into picture in the structure, then it becomes slightly cumbersome by calculating by hand. So we stick to some of the finite element tools to find out the results for us. However, there are some hand calculation methods, some classical methods by which we can determine the different reactions and forces in the structure. Some of the old classical methods were the energy methods, where we calculated the strain energy and considering some unknowns, and then we calculated the end reactions and started back calculating the moments from them. We also had some differential methods, integration methods for calculating the moments and deflections, considering the slope and deflection conditions at different supports or joints, and finding out the results, reactions. Then some new methods came up, like the moment distribution method, which are fairly faster in giving the results for the statically indeterminate structures. So these kind of methods, it depend upon the stiffness, the relative stiffness of the members. So any type of indeterminate structures, the stiffness plays a role, the relative stiffness plays a role in determining the forces in the structure. So we will see in this particular example of a rigid frame which has three supports, three pinned supports. So basically we have six unknowns sorry, two reactions for each support, horizontal and vertical. We also have a varying stiffness in this structure. We have EI as a stiffness in members AB and BD, and E and 1.5 I in members BC and CE, where the modulus of elasticity E and the product of E and I is equal to 102.5 into 10 to the power 3 kilonewton per meter square. Also in this this example, we also have settlements in supports D and E. The settlements are 3 millimeters at support D and 2 millimeters at support E respectively. We will see how to apply these settlements in the structure. Our main objectives for this example today is to find out, first of all, the reactions, the unknown reactions of the three supports, and then to find out all the bending moment diagram for this frame, and also look at the deflection profile, how the members will deflect, how the different nodes will deflect. So we'll look at all these results in this example. So let's start by modeling the structure in the finite element software MIDAS Gen. So that's the blank MIDAS Gen window. We can start by clicking on new project. Okay, so set up the unit system, that's kilonewton meters, from the status bar here, or you can set up the unit system from tools unit system. Okay, then since this type of this example is a 2D analysis example, we go to model, structure type, and change the analysis mode to XZ plane or 2D. Click OK. Okay, then first we start by selecting or defining the top beam of the frame. So let's see what dimensions does it have. So this particular member we are talking about, ABC. So the dimensions are 2 meters, 2 meters, 4 meters, and 2 meters. So we will use the model structure wizard, beam wizard, and we'll enter here 2, 2, 4, 2, and add. We'll use default materials and sections. So material is 1, section is 1, and click OK. So we have got a beam here. I'll change to the front view Okay. Sorry. uh, I will define some materials and section property to these elements. As you know, for the indeterminate structure analysis, it is important that we define the stiffnesses correctly, because everything is dependent upon the relative stiffness of the members. So going back to the model, we have EI and E 1.5 times EI, the two types of stiffnesses in this particular example, where EI stands for 102.5 times 10 to the power 3. So what we'll do is we will assume I as 1 meter square and 1.5 meter square, and E we will take as 102.5 times 10 to the power 3. Oh, and yes, we need to model the columns as well. So let me just quickly drop some columns here. So I'll go to model, elements, extrude, and select this node. So use the select single option, select this node here, and drop a column which is -4 meters in the Z direction, so -4, and apply. And similarly select this particular node and apply -6 and apply. Okay, so we've got the members here. Now close this and go to model, properties, material, add, and we define a user defined material. Material name is material 1, and the modulus of elasticity is 102.5 into 10 to the power 3. Let me check. So that's 102.5 into 10 to the power 3. Okay, and click OK, close. Then we define the properties, section properties. So section, so our first section is I, so name is I. Okay, now what we will do is, since we need only the moment of inertia for calculating the stiffness, so I will not define the database sections. I'll use the value tab. The value tab actually allows you to check or modify any section property directly by entering the values here. So I need not worry about the shape of the section. I can leave everything as blank, doesn't matter. I can name the section as I, and I'll give IYY, which is moment of inertia for calculating bending moment MY. So this moment of inertia is 1 meter squared 4. So 1 is the value of IYY, and I have to give a higher value of area because I want to keep I want to calculate the reaction at this point here. So the columns should have some actual stiffness, some stiffness to resist the actual force or the normal forces, or so to say the reactions. So that means there should be some higher value of stiffness here. So that is only necessary for the finite element analysis. So I'll enter some high value of area, say 100 meters square. Okay, and click apply. So one section is added, which is I. Then we'll add another one, which is 1.5 I. Okay, and change this IYY value to 1.5 and click OK and close this. So we've entered all the materials and sections. Now we need to make sure that the correct sections have been applied to the correct elements. So we go to works tree here, and we find out that all the properties are marked in black, but one of them is blue. Blue in the software means that these sections have not been assigned to any element, so they need to be assigned. So all the elements right now have section number 1, or I, moment of inertia is I. We can check by double clicking. If I double click on this section property, you can see everything is highlighted. So we need to change that. We need to assign the two elements from the right side as 1.5 times I. So we unselect all and we select this element here and this one and this one here. So we have three elements selected, and then we drag and drop 1.5i. So drag and drop like this, and now we can double click to see, oh, this is 1.5i and this is double click, this is I. You can also display the properties on the screen. So if I go to display and go to property and say property name, and click OK, so I can see I 1.5 times I like this. So I'll undisplay this. So we have made sure now that the properties, the stiffnesses are correctly assigned as per the given problem. Now we will go and define the supports and the loads on the top of the structure. So we go to model, boundaries, supports, and we know that the supports that we will be defining in this model, the supports will be all pinned. So we have 3 pinned supports. Okay, so we select the nodes in this manner, select 3 nodes and select dx and dz for the restraint to determine the pinned supports and apply. So these are the pinned supports applied on the structure. Close this, and now we define the forces acting on the structure. So we give the load cases a name. So load, static load case, and give this a name, say P. It's a user defined add. Okay, so basically in this type of structure, in this model, we have 3 types of loads to be added. First is the point loads, the point load 16 and 20 kilonewtons. Second is the uniformly distributed horizontal load, which is 6 kilonewton per meter. And third load case type is or are the settlements at support D and E. So let us apply them one by one. So starting with concentrated forces 16 and 20 kilonewton, going back to the model, loads, nodal loads, and selecting FZ minus 16. Select this node over here, apply, and select this node over here and change minus 16 to minus 20 and apply. Okay, next thing is 12 kilonewton per meter horizontally along the negative x direction. So we go to loads, element beam loads, select this element, this entire element, and change the direction to global x and the value to minus 6, minus because it's in the negative x direction, or applying from from right to the left. I'll just save this model. So save this as example 4 and apply. So that's the minus 6 kilonewton per meter applied. The next thing is applying settlements. So we go to loads and select specified displacement of supports. Select specified displacements. Make sure we have selected DZ or vertical settlement. The value of the settlement is 3 millimeters for this support. So we enter minus 0.003, that is settlement in the downward direction, and apply. Then we select this particular node and we enter minus 0.001, so minus 0.002, yep, 2 millimeters, and apply. Close this, and you can see all the forces that have been, or all the loads that have been applied on the structure are displayed here. Display, that's minus 16 and 20, specified displacement, and the horizontal uniformly distributed load. So now click on the analysis button. So I'll display this and click on the analysis button. Okay, so the structure is analyzed. Let's look at the results one by one. So starting with reactions, reaction forces, fx, yz, because we want to see both horizontal and vertical in the same display. So values, make sure decimal points 2 so that we get an accurate result, and click OK. So these are the reactions in the structure, vertical and horizontal reactions. The next thing is the deflected shape, deformed shapes. So we go to results, results, deformations, displacement, deformed shape, and select dxyz and check on the undeformed shape so that we can compare the results with the undeformed shape as well. And if I click on this box here, I can select real deformations and maybe increase the scale of the deformed shape, so make it 3 times for example. Click OK, and that's how the structure will deform. You can see 3 millimeter settlement occurs here, and the gray line, that is the undeformed shape, and there is you can see how the structure bends, the columns bend, and there is a point of inflection. If you zoom in slightly, you can see, let me just show you the dx diagram so it will be more clear. Yes, so we are focusing only on the horizontal displacements now. You can see the point of inflection here, how the shape is changing. So that's the deformed shape for you. And results, forces, beam diagrams will allow you to see the moments. So beam diagrams my is for the moments, and we'll check off deform. We don't want to see the deformed shape, and we want to see the values at all the locations. Apply. That's the deformed shape. If I click on min max, I can see the minimum and maximum values of the bending moments at different location. So you see that's how the bending moments are changing. Okay, let us now see how the results or how the hand calculations correlate with this type of analysis. So since this is a statically indeterminate structure, the hand calculations do not it's not sufficient to only use the 3 equations of equilibrium. We need some other ways to calculate the forces as well. So that comes so then the other methods, classical methods, come into picture. So let us see the results that we have got here. Okay, so what we have done in this example is done the moment distribution method. So basically fixed end moments are calculated at every member. For each joint we keep the total moment, sum of the total moment should be 0. So here if I scroll down, we have a table, a moment distribution table. Basically distribution factors are calculated. Distribution factors depend upon the relative stiffness of the members at a given joint. So for this joint we calculate the stiffness on the 3 members connected at the joint, and then the relative stiffness is calculated as the stiffness of one member divided by the total stiffness of all the members at this joint, and then we divide the ratio, the stiffness ratio thus calculated between each member, and we get a factor called the distribution factors. So we then calculate the fixed end moments for each member using the simple formulas, like for example if you have, say for example if you have a member which is applied with a point load, and this you can find the fixed end moments using this formula. if it is a uniformly distributed load, you have some other formulas like W square by 12, etc. So using this simple table, we can balance out the moments and carry over the remaining part until and unless we get some good level of convergence, and we end up with some moments here. Now this moment, this type of analysis method is approximate. It will not give you the exact result, because this balancing procedure can carry on forever, and you have to stop upon by making some judgment that up to 2 decimal places, if the convergence is okay, then you can stop the uh, carryover or balancing, and you can get some of the total moments up to that step and get the final bending moment shape. So the final bending moments that you get from the moment distribution method looks like this, okay, which is comparable to the results which we get from the software. So if you check both these diagrams, you'll find that results are more or less similar. The reactions are more or less similar. They are not exactly same, because the moment distribution method does not give you the exact result. If you go on balancing and carrying over the moments, then maybe you will get similar results as the finite element analysis. So this concludes this the video on the statically indeterminate frame analysis with MIDAS Gen. For more topics, stay tuned to the MIDAS UK YouTube page, and all the materials for all the videos can be accessed from the description of those videos. So that's it for now, and thank you.